Hello, everyone. I'm Peizhuo from Chinese Academy of Sciences. I'm very glad to share our work MEA Defender, a robust watermark against model extraction attack. Nowadays, numerous powerful DM models can be trained and obtained by supervised learning and self-supervised learning, such as ResNet, Clip, Sincere, and so on. Usually, large amounts of data and computation resources to pre-train the models. For example, GPT-3 with 175 billion parameters is reported to use 45 TB training data and cost $12 million. Watermark is always used to protect the intellectual property of original owners of such valuable models. Attacker may steal such valuable model by model extraction attack. Specifically, the attacker can force query the victim model to obtain the output predictions, and then generates an extracted model using these queries and predictions. Most importantly, model extraction can effectively remove the watermark embedded in the victim model and generates a clean extracted model, which leads to significant intellectual property infringement of original owner. Existing watermarks can be classified into white box and black box watermarks based on whether the original owner needs access to any parameters or architecture of the certified model during the model retrieval process. Unfortunately, both of them cannot effective cannot effectively verify the ownership of models in the scene. For white box watermark, the extracted model are usually with different parameters and architectures than the original victim model, where the watermarks are embedded, which leads to significant which leads to the failure of watermark retrieval. For black box watermarks, since the samples utilized by the adversary to query the victim model are typically distributed irrelevant to the watermark inputs, most of DM watermarks based on black dot will be removed. In this scenario, we will assume the adversary can only access the victim model in black box manner and aim to steal its using model extraction attacks to remove any embedded watermarks. The adversary can collect some samples of the main task to query the victim model and obtain the corresponding output confidence vectors of these samples. Note that the adversary does not know the architecture of the victim model, so the model architecture used to extract the victim model may be different than that of the victim model. We highlight that if a watermark is designed in a way irrelevant to the main task, watermark will be removed. In contrast, if watermark follows similar distribution to main task in both input domain and output domain, the watermark will survive after such attack. In particular, we design a unique backdoor called a symbiotic backdoor and embed it into the to be protected models as the watermark. Symbiotic backdoor ensures that the input domain and output domain of watermark samples should be in the distribution of those of the main task samples. Input domain represents the data distribution of input samples, and the output domain represents the distribution of output features. On the one hand, such a design indicates the input domain of watermark sample is an indispensable part of that of the main task samples. So the watermark inputs always exist in the samples used by the nurseries to steal the main task from the victim model. On the other hand, the design always indicates the design also indicates the output feature domain of the watermark samples is an indispensable part of that of the main task samples. So the output feature of the watermark will be also extracted by also when they calling the model using their samples. The figure shows the workflow of our approach. In particular, training samples construction will construct the sensor-sized images consisting of features from latest samples. And watermark embedding will show that the feature vector of the watermark samples is in distribution of that of the latest samples. Watermark samples are sensor-sized samples consisting of input features from two samples from two source labels. So we can ensure the input feature of watermarks and this principal part of that of the task samples. Moreover, all such watermark samples are assigned to the target label. That is the watermark label. And the target label is different from any of the two source class labels. There are various approaches available to combine input features of two samples from randomly selected source labels, including autoencoder, based blending, imaging, clouding, and pasting, and so on. So watermarked model trained using the above watermark samples may occasionally recognize some inputs generated by randomly combined samples as the target label. That is also the false positive. Such a phenomenon could help nurseries to learn the existence of watermark in the stolen model and the two source labels watermark to conceal our watermark, and we also collect some samples from the two source labels and combine them in different ways than our watermark generation. Such randomly mixed samples are labeled as one of the true label of the samples used to combine them. With the training data set constructed above, we will aim to inject a watermark into the DNA model or use the above loss function. Our utility guarantees the test performance. Our watermark ensures the watermark embedding. Our revision including the difficulty of detecting our watermark by the nurseries. Our watermark is consisting of two parts: combination loss and watermark verification loss. Combination loss makes the output features of watermark samples are in the distribution of that of task samples by KL divergence loss function. Watermark verification loss makes the watermark model classify the watermark samples to the target label. And our event loss aims to prevent the watermark being misactivated by randomly mixed samples. So we generate some randomly mixed samples and train them to be classified to the ground truth labels rather than the target label. Moreover, to balance the scaling coefficients of task losses, our utility, our watermark, and our variant, we utilize the multitask learning technique (MGDA) for optimization. We evaluate our watermark against the 4 types of model extraction types of 6 models, including both supervised learning model and self-supervised learning model used 5 benchmark datasets. And these datasets cover various tasks in computer vision, natural language processing, speech recognition. So WSR averages at 82.84% for the extracted supervised model and 84.33% for the extracted supervised self-supervised models. These values are significantly higher than 30% threshold required for epically to extract the victim model, so the workflow needs to specify the architecture of the extracted model. However, in realistic scenarios, the adversaries often knowledge of the architecture used by the victim model. Therefore, we also evaluate if our MEA Defender can survive the model extractions in the architecture. So this extracted model is different than the victim model. We specified 3 architectures of victim models and the extracted models from VGG, AlexNet, and ResNet. Table demonstrates that watermarks can always survive the extracted model with an average WSR 63.72%. Furthermore, we find that when the extracted model and the victim model share the same architecture, the WSR is higher than that when they use different architectures as expected. To obtain the extracted model, the adversary must specify the dataset used to query the target model. The distribution of such a query dataset can either be different to or similar to that of the main task of the target model. We apply knockoff against the VGG model trained based on CEPA10 dataset. So we use CEPA10 as an in-distribution query dataset. And for completely auto distribution datasets, we adopt CEPA100 dynamic net and contact datasets. When using an in-distribution dataset as a core dataset, the attacker can serve as its expected model with promising performance. But when auto-distribution dataset are used, the extracted model experiences huge performance degradation. Particularly, the extracted model become almost useless for contact dataset. That is, the main task performance is only 22.51%. Most importantly, our watermark is still effectively it is also effective to verify the ownership with sufficient WSR. Adversaries may want to identify our watermark by randomly mixing samples from any 2 labels and find those that are consistently classified by the extracted model as a specific label other than the 2 source labels where the 2 where the combined samples are coming from. We collect a large amount of randomly mixed samples synthesized from samples any two labels using each of the combination or approach and configuration setting. We measure the probability of randomly mixed samples from each pair of two labels consistently being classified as specific label different than any label of the pair, and then plot the distribution of PRs in the figure. Find that the PRMs synthesized from sample with two source labels used the combination of watermark that combined in different ways than watermark generation. That is the white line, and the white line falls within the distribution of the PMS from any other two labels rather than outer layers. So the adversary cannot detect the existence of our watermark. In summary, we propose a robust watermark approach against mobility suppression attack. That is MEA Defender and we also design a novel symbiotic backdoors to make the input domain of watermark samples within the distribution of the meta samples, and it achieves a high watermark success rate, and the way existing watermarks achieve similar results as ours. Thank you. Thank you very much.